I've now completed making or almost completed making everything, and it works quite well. I'm pleased with it, and there are one or two minor changes that I'm going to need to do, but the concept of it works fine, and using the castings from the water pipes works very well. The only changes that I would make to what I've done is that the lining that I made these of inside here, inside these tees, was not a very good choice of material. I'd be much better off to have done it with a lead-based easy cutting or free cutting mild steel. In the UK it is available, but it's not readily available that I could find at any rate. But it would make the sliding of these surfaces a little easier, but it does work, so I can't complain. You'll see this is an extra addition to what you have seen before. That's because I've made up a plate that can go on here with a chuck on it, so when that's pulled up underneath here, you can index a circle of holes using the drill. Now, one or two things I should really point out, I'll just get this a little bit closer, and we can look in a bit more detail at certain items. It's obvious when you say it now, but the level of return spring has to be just enough and no more to retract it. I've used a Jacobs 1 chuck, which is 0 to, or very small, let's see, it says on there, yes, 0 to a quarter, or 0 to 6.5 millimeters. It's a tiny little chuck, nicely accurate, and I managed to get that to run nice and true. I'll just switch that on just so that I'll just switch that on. So it runs nice and true. I'll just get a drill bit and put it in, you can see that as well. So you can see that does run nice and true. This is the way that the pressure of the downward stroke gets transmitted. This is obviously the lever that you push down to lower the chuck, and on the top of the spindle, which is this here, that's a 10mm piece of silver steel. There sits on top of there, underneath this ring, is a sealed bearing, and basically what happens is that the bearing revolves this whole shaft and is revolved by the collar pulleys, which run by the belt and the motor, and that little channel that you might be able to see just there, yes, you can just see it, that channel is what causes the spindle here to revolve with it, with the pulley. So when this goes down, there are two locating screws which sit inside a groove on the outside of the top hat that sits on top of here, and you can see it's just moving slightly from one side to the other in a rather uncanny kind of way, but that gives us a little degree of freedom of movement, so that it will go up and down and not be sticking at any point. And there's no circular motion transmitted to the top of here. It's transmitted only into the ball race on the underneath. So you're pushing the top hat against the balls in the ball race. And the little sleeve there, the little groove there, there's a little tongue that sticks out of this plate that goes into that, and that is what locates it. Quite a clever design. On most drills, obviously, they have a spindle with many slots in, so it's grooved all the way around, not just in one place. But that's quite adequate for this. This little adjustment here, that's for the stop. So if you screw this screw up, it limits the amount of movement. Now, I reworked a little bit of the original design so that I get slightly more movement than was shown. They didn't actually talk about it in the articles that I and in the book, but people do seem to be concerned about the lack of amount of movement that you get. Well, I got 1¼ inches of travel, which is about 30-35 millimeters, which is quite enough. I don't need any more than that. All the dimensions of this are exactly as they are in the book. I didn't change any of them, but I did change the amount of travel here, and that was worthwhile doing. And if I change this round to this side, you can see some more changes that I made. I made up a new connecting block that goes through here, which allows these pulleys to sit further, both of them to sit further back. I machined a slot out here of about 5 millimeters deep in that direction, and that allowed this to go further down in that direction. So I've got it this way and that way, so that it's lowered the height of that. So it's now pretty near perfect as it is. I made the shaft a little bit longer than was in the book. I added 1 inch to the two sleeves that are shown on the drawings, and that gave me the extra movement that I needed, as well as coping with the positioning of everything here. And when you start this up, the tapping arrangement here is not complete. I haven't made the sleeve to go in here yet because I'm waiting for some steel to come in, but that's a very simple job to do. I can do that easily, but all the hard work's being done now. Now, to do this indexing of a circle that I've mentioned, I've had an old chuck that came off a Tague lathe that I had, or a Tague mill rather, that I had. This is a Kronos plate, division plate, again an old one that I had. These are very good. It's a shame that they don't seem to be available anymore. And what I will be doing is I'll be making up a replacement for this, and I'll drill the holes based off this plate in a piece of 6mm thick aluminium. Goes on there like that, and then all you need to do is to swing this, because it sits right over the top of the middle there. So to do a ring of holes, you just need to mark up the position of the ring of holes that you want here, and then adjust this so it sits right on top of the place you want to drill, and then lock that in. That's then locked on in position. So I could now drill that hole and then advance however many, I can't remember now what this is set up for, to there, to there. If it was 2 holes, I think there's one there. Right, did 1 hole there and then moved it round to there. That's on the other side. But anyway, you get the idea. It enables, say if you wanted to do a lantern pinion for a clock where you've got 10 holes or whatever around the outside of a piece of brass, you could fit it in here and drill the holes for the lantern pinion. It's a nice simple way of doing it. It's very accurate because the centre of this is sitting right underneath the centre of this, and it only moves over by as much as you want it to get to the ring that you want to create. So that I've been pleased enough with, and I'm quite looking forward to getting the tapping spindle done, because that would be a useful addition. I can leave it permanently fixed to the machine. I can use it for drilling. I can use it for doing lantern pinions and things like that, and I can swing over and do whatever I want to do tapping there. I've not got any easy way of doing the tapping. I mostly do that on my ordinary drill press, but it's got a very strong spring-loaded arm, and is a bit tricky to do. So that's as far as I've got. The only thing I've got left to do now, as I say, is the liner for here. That's got to be done. I'm thinking about painting these, so I'll probably paint these grey. But apart from that, it's finished. And I'll probably do some sample drills so that you can see It'll handle up to 1/8 of an inch in steel or brass without any trouble. It will do downwards to very small sizes. I tried under a millimetre, like 0.5 of a millimetre. You just have to be very careful with the amount of pressure you put on, and it's quite a good idea with small size drills and in drills in general for this to have nice fresh newly ground drills so that they cut nicely. It's surprising how much force you need to drill a hole, and it's only when you've got a very light setup like this is that you realise the forces that you're levering down on a drill press normally. Okay, so I'll set up and do a couple of samples so that you can see how it works. This is 1.1 millimetre drill, 1/8 inch thick brass, and I'll run it at half speed, which is about 2,500 RPM. Try it a bit faster. That's one hole. Now I'll switch over to different drill sizes so you can see. I'll do it all in brass to start with. That's 2.5 millimetre drill. I'm just going to drill through now with a 5mm drill. It's unreasonable to expect it to drill a blind hole without any starter hole, so I'll run this now over the hole I've just drilled at the same RPM, and it'll snag and catch just as I get through, I expect. Just a little bit more RPM. There we go. So that's relatively simple. We'll drill a 5mm hole if there's a 2.5mm starter hole, and that's in mild steel. Okay, let's just try the maximum size of hole. Try a 6mm hole, but I think it probably won't manage it, but we'll see. This is over a 2.5mm hole. Right, I'm going to drill 6 holes equally spaced around, starting on the line that I've marked here, and they'll be equally spaced around there at that distance from the centre. Now you can see clearly that there are 6 holes equally spaced, and I started on this hole here. So I suppose I could turn it round and see that they're just back to the same spot, which indeed we are. I didn't bother drilling all the way through because it's quite thickish, this, but yeah, that works fine.